We want to design an op, maybe at least minimum may be necessary. For example, many times CMRR is not specified because one believes for the gains we talk about, bandwidth we talk, CMRR will match requirements. Okay. But if not, you evaluate and figure it out. I again repeat for those who need not make any mistake, DC gain has nothing to do with DC, okay. It's AV0 midband gain. Okay, do I move? Okay, the other parameters to worry about in design are power supply rejection ratio PSRR. The output impedance sometimes is specified. This is sometimes very important, in fact in some larger circuit where impedance matching for the power transfer is very relevant. So sometimes they do specify output impedance. Then one of the major worries which most amplifiers or any analog circuit is worried about is the noise limits, and we will evaluate independently noise. We will have after this, after OTA design, we will discuss noise. Noise is a very interesting noisy area, so it is fun to know about noise, okay. And one who does not understand noise makes noise, so I am the one, okay. So layout area is also one of the constraint. Essentially it comes from the technology node you choose, and the area, if it is a OPAMP is a part of a digital analog mixed circuit, then some area is specified for you, okay. This is the area, then you have to fit in somewhere all of it what they want, okay. So layout area is sometimes the limits. Then there are constraints which I call boundary constraints. For example, any design you choose, the silicon chip if you have to fabricate, the design which you will do it on a specific technology node, because if you are doing SPICE or any cadence simulations including layouts, including schematic and everything, you ought to specify node, because only then you will get technology file, okay. So first thing you have to decide this chip has to be designed on what node, okay. And I keep saying if you are 100% analog chip, do not go beyond 1.8 or below 1.18 microns. Everything is working well with 180 nanometers, and things will start deteriorating as you cross 100 nanometer down, okay. So if you are only looking for analog blocks or analog block, then always prefer 0.25 micron as the best of technologies, cheaper these days by cost. Therefore most of the chips which IIT Bombay student do is only on 0.25 because per mm square cost is the minimum right now, okay. 0.18 it is 1.8 times of 0.25. So 3 lakh ke jagah 5 lakh, so same area. So that is the worry. So node is the first thing you have to decide with. As I said, typically my data from the books which I am using, they have a 0.8 micron data SPICE file. So it does not mean that one cannot design at any other this. You need actual data from the SPICE file whichever node you are using. Since I have copied it from the given book, so they have a 0.8 SPICE file, so which I am just using for my calculations. The second worry for the boundary constraint comes from the threshold voltage available for that node, and what is the beta dash value, that is what is the mobility one gets. This is one of the data SPICE file specifies mu, and of course they also specify oxide thickness, so mu C ox is known both for N channel and P channel, because mu and mu P are separate, so you will get beta N dash and beta P dash. You also ought to know something about the substrate bias parameter is gamma, and also the saturation parameter lambda. Now you will also see that some data which I have given, lambda also is a function of lengths, okay. So at what lengths you are working, even if node is anything, you must figure out what is lambda there. So generally SPICE allows you to know at different lambda values at different lengths, okay. Then you have to specify VDD VSS. Typically technology node almost decides for you what is your VDD and VSS, but it is not compulsory. I can have any requirements, I can create on chip the other biases and can work if necessary, but typically one does not want to do that. We use whatever is given for the node. For the 0.8 microns 5 volts total supply is required, so they generally will make VDD 2.5, VSS minus 2.5, so that the total swing is 5 volts. supply current and the range. There is a maximum current which chip can use under this, because it will start heating. So the R max is also sometime provided, which is not the current you will use in any analysis, but it is it never should exceed that value. Okay, so it's called supply current. Also kind of resistances it assumes, which means what the power supply can it deliver this. Please remember, current can be delivered as per, you may have 3 volt supply, 5 volt supply, but the resistance down decide what current maximum it can draw. So that therefore they specify for given voltage what max current you can draw from the supply. So that you have to know how much is available to you. And then finally the operating temperature range your chip is going to operate. Okay. For all this, giving specified this as well as given the most of the parameters design specs, you can design the OPAMP, and when I say design, my output is the W by L size of all the transistor in the chip. Okay. Because once I get the transistor sizes, layout is relatively simple, automation can be done and you will be able to actually design the chip. So our output as far as the design course is concerned is the size. Further ahead many other things are important, but this is the output from our side, that is the end for us. Okay, so as I said, these are constraints, those are specs. We have already seen this circuit. I will repeat again, slightly modified one, not really modified, only bias circuit has been added. This is my single ended 2-stage DFAM plus gain stage, and this is the biasing circuit. This R can be replaced by diode if necessary, and so this is your actually current, bias current you are creating. Now many times you need voltages. Okay, let us say you want to bias with VB. Okay, so I put 2 diodes, each will have some voltage drop. So VDD minus that, and will at this current what W by L you choose, I can decide what drops it has. So I can create a V bias of my choice. I may put even 3. Okay. So but to know all that W by L for them, I need current, and current comes from M4, okay, or M9. Okay, sorry. You must be observing these are M1, M2 are the input stage, M3, M4 are the current diode connected loads. The current is created out of M5 from the mirror side. So this is your ISS current going through M5. This is the C1 capacitance which we discussed, and there is this feedback Miller capacitance CC, and then there is a gain stage M6, M7 forms the gain stage, and the output capacitance which includes load. So that is our C2. Now you must be finding out that somewhere I did not put some number. Which number I missed? 1, 2, 3, 4, 5, 6, 7, 9. So 8 I have missed. So somewhere 8 is going to come. Okay. So I just left that right now. Additional resistance will be required, and we will see where that will come. So one can find, if you know VDD and you know the W by L, we know from this what current it is flowing through. This minus this divided by R is the current. VJs of this and these are same. This is a current mirror, so nothing great happens. So whatever current is here can be transferred here. Excess voltage is generally known for N channels for given technology. So use that. So you will be able to get the currents in this arm, and size wise it will give you whatever current you want in M9. Normally M9 currents are same as M12, and then increase ahead whatever currents people are asking. So this basic mirror is not really great, but normally same size, voltage is created out of the diode drops. Okay, and to get this drop, you know what, you need current. So you know this current is this, so you can figure out what drops. VDD minus that is your VB. So for example, tomorrow you want to bias this as a current source M3, M4, you can create V bias of your choice and actually connect there. Is that clear to you? So why I use this? Because in case tomorrow you want double-ended outputs and you have a current source biasing, you can use one of the bias points to reach there. If you want very finicky about this, that this voltage is not very good, what should I put there instead? A band gap reference can be introduced there, and that voltage can be used for even stricter control on VB. But simply this is good enough in many cases. So this is the circuit which we want to design. No. I just now said, Baba. In case tomorrow you want a current biasing, then you need VB. So the bias circuit is normally kept common for everyone. Wherever whosoever wants, you can pick up whatever he wants. This is general. In our case, this whole arm may not be there. We can directly, you can leave M9, M10, M11 full arm actually, okay. You can directly form M5 this to M5. So it's not that it's necessary, but general biasing we do keep additional arm, and there we actually use the same currents and figure out what bias I can create. Okay, so is that clear to you? I will not right now design for you the value of M10, M11, M9, M12. This can be independently handled as bias circuit, and we will not right now in our OPAMP design to first extent, we will not design the mirror part, because which we can anyway independently design. This has nothing to do with ahead, so that can be independently designed. But just to show you that how much circuitry is essentially in an OPAMP is connected there. You are right, you are good question, but I just now said this is a general biasing scheme. P-bias is not used by me, but tomorrow let us say I do not want diode connected load and I want current source loads. I need bias, so I will use this. So this is independently created and used whenever you want different bias, you put different diodes. Is that clear? You can have another arm and put 3 diodes there, or maybe 4, whatever it is, and you can create different VB values to actually suit your different circuit requirements wherever it goes. But this is not redesigned, it always comes once and reused every time, okay. Okay, so this is my circuit which I want to design. So I will like to define design for given specifications. You will now start the value of W by L for M1, M2, M3, M4, M5, M6 and M7. This is what output of my design will be, okay. Is that okay? So this is what we are going to, so on what specs we want to design? Everyone drawn the circuit? This morning only I have drawn, except that this part, the rest circuit is same. Also I said you this CC is, I have connected, I knew it because I want stability anyway, I want to split. So I am going to put it, the value I may now choose how much it should be, okay. That is the only thing. But otherwise I will not go by CGD, I will actually put CC there, okay. Is that okay? So we go for the specs now. These are arbitrary specs, nothing very great, but typical specs, and these are good enough specs in many requirements. You have a DC gain, I want more than 4000, and I keep telling you that the values are not specified in design exact numbers. No one says 4972, no one says so, okay. I want a gain, DC gain, which should be larger than 4000, okay.
The product is really mentioned what is
it? They do. No, the design itself they will say how much for gain for, OPAMP is designed for a gain value actually, gain greater than something. The reason is that when you design a chip circuit with this OPAMP, you should only use 4000. That is called over design. It may be 4000, 5000 also. Is that correct? But not just that, during the design itself I may go any other value than 4000, because the spec says that not less than 4000. So I have now a parameter which I can play with. Okay, for some other specs to meet, I figure out that AV0 should be 4500, so I will put 4500, because the design says it should not be less than 4000. So I meet those specs anyway. But once I designed it, once I got it, those specs are fixed. Once chip is this done, then it is not changed again and again, okay. Till you fix, you have the parameter to vary on. Then the power supply is 2.5 VDD and minus 2.5 VSS, okay. So you have total current, total swing of 5. I have a gain bandwidth requirement is 6 megahertz. Then I have a load capacitance which is C2 in our case, okay, which is 10 puff. So all other capacitance plus CL all adds up to 10 puff. Okay, so don't just go by CL, it said total C2 is 10 puff. Alternatively, you evaluate the without CL all the values by the formula we gave and add the external CL value and say that is C2 now. Okay. That okay. For evaluation right now some number is chosen which is higher enough compared to others. We are also told this minimum slew rate should be 10 volt per microsecond. That is the output voltage should rise in a microsecond up to 10 volts. Okay, that is called slew rate. So we are dV0 by dV minimum required is 10 volt per microsecond. Then the output swing, this is also interesting parameter. We want output to be, though the power supply is 2.5 minus 2.5, the at least output swing between minus 2 and plus 2. Okay. Then ICMR, which is common mode input common mode range, V in max, V in min. So V in min is 1.15. Okay. Slightly not correctly shown, but it's 1.15 volt. You will be figuring out that if I increase to 1.5, it will not be satisfying saturation. So I first thought 1.5, then I looked at it, I said reduce, put one extra there. That's the way it is. Okay. Because I didn't have spec somewhere, so I just thinking, I said, oh, calculator nahi aata hai, one डाल दिया, ठीक हो गया. But that gives me 0.35 shifts, so that's good enough. Okay. And the maximum V in maximum is 2 volts available to you. Power dissipation, P dissipation is less than 2.5 milliwatts. This includes power in the bias circuit, power in the DFAM and power in this. Sometimes we may specify only in the DFAM and gain stage. So right now, as I said, since bias circuit was not part of my design, so this value does not include power coming from the bias. But in real life, the power dissipation includes power in the bias circuit, power in the DFAM circuit, power in the gain stage circuit, and in real OPAMP there will be a buffer stage, power in the buffer stage circuit, which may be even higher. So actual power dissipation is sum of 4 amps, okay, and that you have to use. And then the way is you should start allocating, okay, how much arm I should give, okay, so that net is within this, and then try to adjust, then keep varying which suits most of that, okay, that's how it's apportioned. So currents are apportioned each arm, okay. Right now for us we are taking simpler issue, so only 2 arms, DFAM, and so I don't have to apportion, I will evaluate what current going through the other, and therefore I will be able to tell you what is the net power dissipation, which I believe should be less than 2.5. So it can be 2 volt, 1.5 volt, okay, or it can be 1 milliwatt, sorry, not volt. It's fantastic, but that if you do this, whether you reach this or whether you reach this, you verify. If that still satisfies, fantastic. Lower the power, better is the design. Okay. Another worry which is so far this morning we have been talking is whether the OPAMP design has good stability, and that we must verify. Essentially what does this mean? What phase margin I choose, okay, for relatively good stability. So that is my design spec, I am deciding it, what FIM I should use. Design output, again for all 12 transistors I need to know W by S, and node I am using is, the reason why I say that data which I will show you now is taken for this, okay, 0.8 microns CMOS. Is that okay? So these are my specs, this is something I believe I should know, which I will fix, and this is something I will derive at the end, okay. 2.5 VDD, minus 2.5 PSS is available for 0.8 microns, 5 microns, 5 volt swing, okay. All 0.8 analog circuits allow you for 2.5, actually higher the node, higher is the voltage. 0.8 is almost close to 1, so it is anyway higher actually. Why I choose 5? Because there is, we are not using it, it is a short channel device, so some effects of short channel are seen, which in our calculations we will not use it, SPICE will take care of many of those parameters, okay. Okay, It's a very good question. Try it yourself for the sake of brevity. Why people at all go for minus 2.5 or minus to plus? Why dual rail? Why not ground and VDD? Hmm? So there is something advantage I get by doing this. Those swings still I get 5. Okay. So क्यों मैं माइनस के इतना बहुत खुश हूँ? थोड़ा आप सोचो, नहीं तो नेक्स्ट टाइम कभी बताएंगे. जरा सोचो कि everyone, no, not just the something he said, there is something to do with noise. Okay, so I give you some noise on that. Okay, always analog circuits, unless it is single ended power supply requirement comes, some op-amps do say only one, otherwise you must see all op-amps show 2 terminals, that is the idea. All general purpose will have VDD VSS. Only specific op-amps which use only specific requirements, they may use single ended power supply. Okay. These are the 0.8 micron node spec taken from a SPICE file. Actually this was not 0.7 but I made it equal. VTM is 0.7 and 0.7 minus 0.7 is VTP. Another thing which I have not stated but I will use in the end, which I now want to say, the VTs are, there are actually VTs are not specified as single values. They will specify, or rather sometimes you may have to figure out in case they are not, what is VT maximum and what is VT minimum. Okay. Now max min values can be because of variation in process, temperature, and also bias, substrate bias if it goes through. So VT varies with substrate bias, VT varies with variation in process, and VT varies with temperature. So in real life when we design a circuit we go for the bounds. So we do use max and min values of VTs, and in this case it is found typically 0.1 plus minus 0.15 volts is chosen as possible variation. So for example this may be 0.55 and the max may be 0.85. Okay. Why I need these values? Because if you see the voltages ICMR, say VO max or V minimum or V in minimum. So at that time what maximum and minimum I should use out of VT which will guarantee me this min or max values. Okay. So otherwise the W by L size will be very different from the real life. Okay. So I just told you in real life this delta on this is specified. Okay. If not you have to actually generate by simulate karte hue 4 corners design karo or figure out what max min you will get. Okay. But generally in course I will tell you what is the max min. Okay. तो आप डिज़ाइन के फीचर समझ में आए. डिज़ाइन करते समय चारों दोनों आँखें, दोनों कान, दोनों हाथ सब मैक्सिमम पीक पे होना पड़ते हैं. Okay, so beta and dash is 110 10 to the power minus 6 amps per volt square, and gamma for n channels, gamma is the substrate bias factor which is 0.4 root volt, and beta p dash is 15 10 to the power minus 6. So we are roughly expecting 2.2 ratio of mobilities, and gamma p is 0.57 per root, not per root volt. Then again the SPICE file if you see they say lambda n is 0.014 and 0.01 as lambda increase from 1 to 2. Okay. Similarly lambda p goes from 0.05 to 0.01, length goes from 1 micron to 2 micron. So each SPICE file will specify you. You go see full model files and not necessarily in the NG SPICE you have, but the level 9 BSIM models will specify you what max min it will go through. Our case we choose one of the values and probably solve something, but in simulation why should it should figure it out what is it and it should solve. Okay, so I just gave you in real life these values are chosen by program and not by you, it will actually pick up the value. 2 phi n, since you are not calculating, so I did not give Tox etc, that also I should specify Cox and everything, but I didn't. But anyway just Fermi potentials are given to you for n channel and p channel. We also wish to tell you that in most cases where the device is in saturation, I will assume for calculation of VGS, lambda is small and therefore I use VGS is Vt plus VOV or Vt plus under root 2 IDS by beta. This is the expressions I will use. Accuracy probably is a bit of lost, but if it is lower values it does not matter. Okay. So if longer, that is why I keep saying the longer length everything is fine, shorter length all worries, okay, except something I said last time, it helps you a lot. Okay, is that okay? Specs you are written, these are the process specs which will be specified to you, okay, and this is actually taken from a SPICE file for a 0.8 micron, okay, CMOS file. So I have not added, subtracted anything which they have said. If they are wrong, the company which is manufacturing, they are wrong data, I do not have. Okay. For me it does not matter what value I get, I will get instead of W by 4 I may get 16, or they wanted 16 I may get 4. For me how to get is more relevant. So as of now, but with these specs which are standard I am told, this should be relatively correct values. Okay, we have already done this morning the equivalent circuit using Miller capacitance. There is GM V1, C1, RO2, that is C1, C2 we already specified what are those. Now please remember C2 includes CL, or rather C2 is CL or total. And we also believe that in DFAM M1 and M2 are identical, that is our starting with DFAM, because otherwise there will be a huge issues. So M1 M2 are identical, so GM1 is equal to GM2, both W bar and thresholds are same for n-channel transistor forming DFAMs. Then we say M9 to M12 as I just now showed constitute the biasing circuitry with resistor R, which could be a diode, for bias current control, which right now as I say I am not designing, which I can independently design for you, but this is something which immediately I am not designing, I am only designing DFAM stage and gain stage, that W by L. But once I know what I want, I can go back and figure out what I should push. So how we know the data, we know the specs, we also know that it should be stable, okay. So all these things which I said have been known to me. I also decided the schematic, that this is the circuit I want to design. Right now I have chosen this, in real life this is not specified. So you may have to even decide what circuit you should use. But generally single-ended op-amps, single-ended output stages are used, DFAMs are used for a normal gain stage op-amp. 741 and all series have single-ended outputs. The differential op-amp as they call it is essentially two-ended outputs, okay. So right now we will not go into that, okay. Maybe we need it where there are issues, something what op-amp you have done in second year or third year, I do not know, where do you see analog lab, second year isn't it. There is one experiment we ask you to find out offset voltages. So between the two inputs, if I do not apply, the output should be 0, but it is not. So you apply a difference, some opposite, so that V0 goes down. So one technique of offset cancellation is using a different system, okay. So that is why I say it is used many a times for offset cancellation inside chip, not externally. Inside we will do something so that offsets are 0, okay. No one puts two resistors, हाँ, जो बाहर से करते हो आप, क्योंकि अंदर ट्यून करने के लिए कुछ जगह नहीं है ना, बाहर तो आप स्पॉट को घुमाते हो, वहाँ क्या करेंगे, तो इसलिए वहाँ कुछ नहीं कर सकते. Please remember what you can do on the board, I cannot do anything on chip. So you must plan everything fixed and then think it's still programmable, okay. Okay. So here is, so let's start. Now so far so good. The first thing, my worries are always for any amplifier is how much stable it will be, okay. And this morning I have with great fanfare said that as long as your phase margins is 45 degree and up to 70 degree, we believe the op-amp will or amplifier will remain stable. And I have explained you this morning enough that anything lower or higher what it can create. So therefore this is typical range of phi m which I am going to use in design as a spec, as a parameter, is that clear? So I can choose 45, I can choose 50, I can choose 55, I can use 60, 65, 70, any of these values is within my control. I should decide, oh 60 is good enough for me, that is fair enough for you. If you say no, I want minimum 65, you take 65. If you choose different, all the other values will correspondingly shift, because that W by GB by P and P2 will change. So everything will change, does not matter, some other W by L will appear, but you must decide the margin for you. So I had chosen these 3 values for initial calculations. The final design is for 60, but I just show you how much variation the poles will get if I choose 50, if I choose 60, or if I choose 70. Please take it, even 75 is not out of question, but as I said you, it creates some other problems, and therefore preferably keep to 70. For the given op-amp circuit, since it is 2 stage with 2 capacitance, and there is third capacitance, we will today calculate that value, the C3, which is for the DFAM side. Can you, before you write down, can you quickly tell me what will be the pole there? Just see it. No, this you write down, then I will tell you what this C3 capacitance which is coming there may give you a pole and a 0. C3 is in the DFAM inside, that is at the M3 M4 stage there is a capacitance. Look at this, M3 M4 has CGS sitting there na, so that may create a pole and also 0 because it is a feedback, okay. So it may have a pole and a 0. What is the criteria? The criteria is, because of this, the values which you are going to get, if they are larger than say 100 times or 500 times the gain bandwidth value, then I say it is damn care. Okay. Otherwise, you will have to worry about what is the third pole is going to give you. Okay. 99% or 99.99%, the CGS values are so small that typically, for example, 6 megahertz you are asking gain bandwidth. I evaluated, probably I do not know whether I reached there today, it will be around 900 megahertz will come as your pole frequency. Okay. So 900 megahertz for a 6 megahertz gain bandwidth is far away. Okay. So when by the time 900 megahertz frequency comes, the gain would have gone to some 1000 dB, minus 1000 dB kind of thing. So we are least worried about such poles and zeros. Okay. However, this is not to be taken without just saying evaluate, figure it out. If it comes, fair enough. If not, think of it, what do I do now? Okay.
So we have to figure it out from technology data.
Yeah, CGS is given from technology. Spice file gives you all capacitances. Spice file gives you everything. Currents are decided by you, so GM you get it, and GM by CGS you have to evaluate. Okay, so that the pole you have to figure it out. Okay. I will show you value of calculation of that for given betas, given values, and the way I calculated it around 930 megahertz. Okay, so which is far away in my opinion, but I will check again. Mera mistake ho sakta hai, but I hope so it is. Normally no one takes, so obviously must be right. Okay. We know phase margins is 180 minus tan inverse omega by P1 minus tan inverse omega by 2, and this morning there was issue plus tan inverse Z1 by W, but when it goes the other side it becomes tan inverse Z by W by Z1. So, and we know again, I think I am making same mistake again and again. This is only phi, and phi m will become when omega is gain bandwidth value. Okay. So phi m is 180 minus tan inverse GBW by P1 minus tan inverse GBW by P2 minus tan inverse GBW by Z1. Okay. We also said this morning that typically we expect the 0. This morning we have plot the sigma j omega axis plots, and we have seen that the 0 should be on the right half plane and as far away as possible from GBW. Is that clear? What is the criteria we said then? Because by the time 0 appears, the gain should have fallen much larger in negative values. Okay. If minus 100 dB, you add 20 dB, it does not matter. But minus 20 dB, if it adds, it becomes 0 dB. So that may create phase issues. Is that clear? So we have already said the 0 should be quite far away from the gain bandwidth value. Okay, how much we will check. Okay, tentatively we can say 10 times the gain bandwidth times 10 is what the 0 could be. Okay, but I have solved for all 4 cases, 4 passival cases. So 0 is at a frequency which is 10 times the GBW. This ensures that 0 occurs only when, due to both poles, gain falls to minus 40 per decade around 100 dB, minus 100 dB, and then 0 appears. Okay. That is, as long as it goes to large minus this, it does not influence. So this is now what we can do. What we can start choosing? Phi m. Okay. So how many phi m's I have chosen? 3 values. So I will evaluate for 3 values this, and I will also use some 4 or 5 values for Z1. Okay. So combination. Okay, 5 3 15. So I did this calculation, I will show you. Okay. So what I will get from there is interesting to me. Everyone has written down? Please note down. ये लिखने की जरूरत नहीं, ये आपको आना चाहिए, ये जरूरी है. Okay, so is that okay? This statement is okay that I am having 3 values of phi m, and I will also choose different value of Z1 and figure it out what is the value of P1, P2. Let us see what is P1, P2, it will come soon. Okay, is that everyone has written down? Let us say case of phi m 60 degrees. So this is also 180 degrees. If I have not put zeros, degrees, put everywhere degrees. Okay, as long as I might have missed some places. So 60 degree is equal to 180 minus GBW by P1. This is the expression which we are going to use. Okay. Now we see that AV0 is 4000. Is that correct? So what is P1? The bandwidth. So what is gain bandwidth? P1 into AV0. Is that clear? Gain into bandwidth. Na? So gain is 4000 minimum plus bandwidth of P1. Okay. So gain bandwidth divided by P1 is AV0. Is that correct? So AV0. Now if I take tan inverse of gain bandwidth by P1, I am essentially saying take tan inverse of AV0. Is that correct? And AV0 is order of 10 to power 4. So tan inverse 10 to power 4 क्या होता है? 90 degree. It's like infinite. Okay. So 90 degree. तो ये जो पहला था वो टर्म तो इतना आसानी से निकल गया हाथ से, है ना? So ये this term is taken care. So now we say, let's say now Z is chosen as 10 times the gain bandwidth. So if I choose that, then I said tan inverse this by this is tan inverse 0.1, which is 5.7 degree by my calculator. Hopefully it is correct. Okay. So I got now 120 degree is equal to 90 degree plus tan inverse gain bandwidth by P2 plus 5.7. Is that correct? I substituted this and I substituted this. So I got this. So what do I get? Therefore tan inverse GBW by P2 I got now. Everyone has written down? Please write down this expression. This is what we are going to. ये 30 है, उसमें से 5.7 गया तो 24.3. Okay. So tan inverse GBW by P2 is 24.3. So उसका tan निकाल देंगे ना, तो GBW by P2 हो जाएगा. Everyone noted down? So now we are getting some feel ना कि how many calculations you need to really, still there is nowhere we are close to W by S, we are just struggling to reach there. You know. So I get GBW by P2 is tan of 24.3 which is 0.45. Okay, 0.4545 और कुछ होगा but roughly 0.45. थोड़ा ज़्यादा है क्योंकि मैंने उसका इन्वर्स जब किया था वो 2.2 आया है, तो वो थोड़ा आगे भी होगा कुछ, क्योंकि वो x-1 किया तो 2.2 दिखा, इसलिए मैं लग रहा हूँ कि वो थोड़े डेसिमल आगे कुछ और होंगे. So now we have many options. One is why we chose 4000. We can choose higher, but as far as tan inverse comes, it doesn't matter because वो 90 आने वाला है. So यहाँ और भी कुछ value यहाँ रख लें तो it doesn't matter for me as far as tan inverse AV0 is concerned. 4000 or 5000 or 8000 doesn't matter. But you can still have a choice now which you may use later. Okay, so it's not necessary. We are not worried now. How much should be? It can be anything. 4000 you say limit, okay, it's enough for me. Now we can also say Z1 can be any other value. Why 10? So I have many other values. I said okay, why I have actually gone up to 100 times GBW. So I say 5 times, 10 times, 20 times, 50 times, 100 times. distance away from 0. Okay. So I have many values of Z1 which I can use, which is in my control. Okay. I can decide what value I should push. I have 3 values of phi m. So I have 50, 60 and 70. So I have 3 values of this, and let us say I choose 5 Z1. So I have table of 15. So I have 5 Z1 values, 3 phi m values, and then I can calculate this P2 for any one of them. Is that clear to you? What is the technique I am following? So this is essentially, let us say for example if I use 0.05, sorry, it is 100, this is how much? 0.05 is 1 by 20 like this will come 0.51. So you keep changing the Z1 value, and correspondingly this term will keep changing, and I will have a table to show you later. So Kale, do you get design word now? That we have options means you are designing, you are trying to fit what you want. Okay, is that okay everyone? So I did this calculation for you, since I had a calculator, so I did. The P2 will be 1.47 GB if I use 10 times, 1.31 gain bandwidth if it is 50, 1.85 if it is 5 times, and 1.19 into GB if it is 100 times the gain bit. All that it will tan inverse that Z by W changes, so I subtract and again then I figure out what is the tan of that, and then I get these values. So you can see Z can be between 100 this and this. So pole can vary. Why I am interested in pole 2? Because phi m was decided by pole 2, and from the phi m only I am now getting that value of pole which satisfies my phi m by making a choice of Z1, okay, which I have 5 choices to make. Okay. So from 1.85 to 1.19 times gain bandwidth, it can vary if I change the 0 from 5 times to 100 times. But you can see even if I change very drastically, these values are not changing as much. Is that clear? So typically 10 times, 20 times should be good enough in most cases. But just to get an idea that even if I go 100 times too far, what values I am going to get. Okay. So I just did evaluation for you. Everyone? If I do it for 50, instead of this I can get 130 now, the first time will be 90, and again this can be Z1, Z2, Z3, Z4, Z5. So correspondingly I can calculate the value of P2 for this phase margin for 5 values of Z1, Z2, Z3, Z4, Z5. So I did it for 60 degree, I am showing you for 50 degree, and finally I will do it for 70 degree. So you will find that this does not very much changes very much, but something else changes because because of larger phase margin, GM may be different or the CC value you choose may be different, and that may create further problems in some other poles. Slew rate for example. So do not think that this small change means small change somewhere maybe 10 times somewhere else. Okay. So decision is how much. Have you any time seen a data book for any specification? They say typical, minimum, maximum. 60 degree is typical. Okay. So we will do this 50, 70 can be min max. Okay. Okay. Has anyone noted down? P2 GBWY can be 0.76, 0.68, 0.84, 0.54, depends on the Z1 values I choose. Okay. If I use this 70 degree as phase margin, so 180 minus this, if I subtract it 110, this will be 90, so 20 minus this, and I calculated for 5 values of Z1 again and figured out the ratio of gain bandwidth to P2 as 0.2, 0.25, 0.536. Okay, you write down this. Of course, these are not very relevant numbers, just to show you if I am a designer, you can do in simulation everything is fine. But when you are not doing simulation, or rather when you want to start simulation, first get hold of around what you should simulate. Okay. Otherwise too many specifications, too many parameters to handle. it can go haywire. Okay. So do not try mischiefs. Okay, so here is the table which I created. Phase margin, 4 values of Z1 and correspondingly P2 values with reference to this. All that calculations which I showed you earlier are summarized in this table. You can even write a small program and just continuous value change, everything can be printed in 15 minutes. Hand में time लगता है. There is no transcendental equation, there is no second order equation, there is no non-linearity, simple calculations. Problem किस में आता है? dn by dt is dj by dx, time space variant, continuity equation है ना, वो प्रॉब्लम एक टाइम फ्रेम में एक दूसरा स्पेस फ्रेम में, तब थोड़ा सोचना पड़ता है कैसा सॉल्व करेंगे, उसमें फिर पॉइजन्स इक्वेशन रो बाय एप्सिलॉन वो ऐड करो तो और एक नॉन लीनियर लेके आएगा, then that requires numerical. Okay, if that table is written down, as I said, this table does not give you any great information, it is only trying to tell you how things change if I change phi m or z1. So I can actually evaluate for any phi m, for any z1, what should be the size, what should be on my P2. Is that clear? Now you may have to try few of them in real design and check, but as I say, I am going to do for 60 degree at 10 GB. So one value I will use, but I say I have access to any value of this kind and I can still start design on. Okay. You can see roughly, except this first one, almost everyone is around 2. So it is not that it is changing drastically in great numbers. So it is okay. But in this it may change. If you go from 50 to 70, things change. But on the same phase margin, it is not that great change. So you can choose 10, 20 is okay, whatever you choose. Is that okay? So having done this, we now state the case, typical value of phi m equal to 60 and Z1 of 10 times the gain bandwidth. So I got from this from the table now, the second pole is 2.2 into gain bandwidth. Is that clear? Just now I got it. So I say second pole should be 2.2 times that of gain bandwidth. Okay. For 0 has been adjusted to 10 times the gain bandwidth and phase margin chosen is 60 degree. This morning I discussed so much about 60. Okay. Z1 is a pole you have to fix, because today I said right hand pole we never worry, but now I am saying that control also helps. Okay. In design, as many controls you get, better for you, because one may change drastically, so the other can be used to not allow this to change drastically. So as many parameters you hold, that is better control for you. Okay. Away from the GBW point, from 5 times to 100 times I checked it. I find 10 is normally good enough for my evaluation, so I chose 10. But you may start with 20 and get away, not much will happen. Okay, so for this case, what is the P2 pole we calculated from the expression GM6 by C2, okay, GM6 by P2, and typically this value, what does it say? Actually it does not say equal, what should it show? The pole should be larger than this value, so that 60 degrees guaranteed for you, is that correct? So the minimum is equal to, but anything above is also acceptable to us. Okay. So GM6 by C2 should be greater than 2.2. What is the gain bandwidth product? GM1 by CC. Okay. So if you do this from this inequality, I want CC should be greater than 2.2 GM1 C2 upon GM6. What is the effort going on? For this phase margin, what is the value of CC I want to know, okay, at least in terms of C2 if not. C2 is given to me 10 puff. If I can get the ratio of this and if I know this, I know what should be the minimum value of C2 I should hold, okay. Is that okay? What I am looking for, the value of CC which will give me 60 degree plus phase margin when I put 0 up 10 times the gain bandwidth. So if I do this, since I said Z1 is 10 times the gain bandwidth, Z is GM6 by Cc, and that should be greater than 10 times gain bandwidth G1 by Cc, both Cc, please take it. So GM1 by GM6 will be less than 0.1, okay, or equal to 0.1. Is that okay? Since this is the inequality, GM1 by GM6 should be less than 0.1 or equal to 0.1, that's the possible. Now this value I can get, this is specified for me, okay. So then what do I calculate? I can calculate Cc value, is that correct? Because that is one spec which I didn't know how much to put Cc. So now I have figured it out, I can evaluate Cc. If it is 5 times, I get Gm1 by Gm2 should be less than 0.2, 10 times it is, just now I calculated it should be 0.1 times. So typically for 10 times gain bandwidth as Z1, the Cc should be larger than 2.2 into 0.1 into C2, put everything value here, so Cc should be greater than 0.22 C2, okay. कितना होगा फिर, C2 कितना है, 10 puff, okay. C2 is given to you as 10 puff, so Cc कितना होना चाहिए, 2.2 puff से ज़्यादा होना चाहिए. अब इसे 2.5 ले सकते हो, 3 ले सकते हो, ज़्यादा होना चाहिए. So I know which is the minimum Cc I must use, so that 60-degree phase margin is guaranteed when I put my 0 at 10 times the gain bandwidth, okay. So one of the features of evaluation was, अभी तक हमने W/L के तरफ गए ही नहीं है, अभी तो हम सिर्फ पैराफेलनिया पे ही हैं, Cc क्या है, हाँ. So this fact has to be understood by you, that its most important part for you is to know what is the Cc values, okay. अब design क्या, what is done in design, then you may choose value yourself. 2.2 is the minimum, you may choose 2.5, you may choose 3, 5, then you see 5, what will happen? So then you come, oh no, 2.5 is okay. That is what the design specs is trying to tell. Before I go to the actual evaluations, what is my figure of amplifier, before I leave this, before I start calculating W/Ls, please remember I have now calculated this, which is what I say is requirement for amplifier to be stable. Now I figure out that there is a C3 capacitance sitting here, which is essentially CGS related, okay. Why CGS? Because CGD is shorted. This is a P channel device, so don't say CGD कितना है, CGD short कर रखा है इधर, है ना, सिर्फ CGS input पर है. Now if you want to see CGS or what we call C3, so there are one pole which will come because of this resistance. What is this resistance? 1 by Gm3, okay. So if I calculate the input pole for C3, it is minus Gm3 by C3, and if write expression for output to this, I will get a 0 which is minus 2 Gm3 by C3. So here, but what is the sign of 0? Minus. What is the sign of 0 pole? Minus. So both are lying now on the left of plane. So they are least worried because they may cancel now. एक 20 dB ऐसा जाएगा, उसी उसके पास में ये नीचे आना शुरू होगा, तो एक दूसरे के लिए वो कुछ भी काम के नहीं है. So essentially we may now say, if my P3 is much larger than P1, P2 and Z3 is also much larger than P2, which I got it in fact, as I say 900 odd megahertz, then the use of this poles and zeros is not of any relevance in further calculation, though we may have to evaluate to verify, okay. But just to tell you where from we verify, just this substitution here, I must get Gm3, I must get this value of CGS whatever I get, and correspondingly evaluate these two and figure it out where is the poles and zeros going up, okay. And if that happens to be too far away 1000 times, we damn care about it, okay. So this is an issue which you must address, though as I say, if you don't address, nothing goes wrong in 99 cases, but as a designer I cannot accept anything without seeing it, okay, though my intuition says it will not affect. So this is an important, because we keep talking, we are designing, how do we create a right half plane 0 or left half plane shift it to 0, एक resistance चाहिए ना. So next time when we design, we will try to see somewhere instead of C it should be R and C, series of that, and once we get it, much of this 0 on the right hand side can also be handled by us. That is the next stage which we will have to do it. Right now I assume that without anything phi and 60 degrees achievable with whatever values I choose, but in case there is an issue further, I may actually start looking at 0 also. इसको इधर लाऊं क्या, उसी पोल पे बिठाऊं क्या, ऐसा I कैंसल कर दूंगा मैं उसको. ओके, मिलर का तो बढ़ाना, I don't want to increase CC, that I knew. If I increase then I have more issues. So I said okay, CC I kept this, now I bring this pole 0 on the pole and cancel it, nulling the effect. So we will do that, but before last slide I may like to show, I just want to show you that there is another P3 Z3 available, but in most cases we never bother about them. But as a designer I thought we must show you that yeah, there is a pole and 0 which you must evaluate, and if it is extremely away, forget it, okay, which will happen. Why it will happen? Because CGS is so low, the GM by CGS is very high frequency, so don't worry too much. Because CGS compared to all other capacitors is very low, everything is safe for you, okay, at least it will be like that, unless the size of that transistor is so big that the CGS value boosts up, and then that pole may come, okay. So if it is 100 आ गया size का, so then you have to worry about this pole as well, okay, pole 0. If I continue my design, at least this sheet will finish and will stop. We say C2 is given to 10 puff, CC is taken to 0.22 C2, so we say CC should be greater than 2.2 puff. So I can choose 2.5 puff, I can choose 3 puff, I can also choose 3.5 puff if I need, okay. I have calculated both for 2.5, why I chose, because it is close to 2.2. So I thought okay, one value should be as close to this, the other is little away from it, okay. So that designer should actually evaluate both. 3 is of course not too close, but still too far, but still. Now you look at this figure again and again, that figure is very important. You note down and then I will show you the figure. Okay. Our requirement came, CC should be greater than 2.2 puff, and then I have a choice to make. Is it okay? Yeah, इसके बारे में when I will show the figure and come back. Okay. You just write down, think of this. Right now just forget this, first only write down CC values are 2.5 or 3 puff, one can choose even higher, but I have chosen only 2 to evaluate, okay. I will come back to it, 1 minute. So what I see now, this CC value is connected to the output of the define stage, is that correct? So if this is to be charged faster, okay, that is slew rate for this, then I must see that the current which can allow this CC to get, the current is only provided from this arm, is that correct? Now the maximum current which any of the arm can get is how much? When this is off, this is on, so the maximum current which this can provide here is only I5, IDS 5, is that correct? To charge this, this is the only current available to you, is that correct? Full of it, because in midpoint it is half, but the maximum possible is one current which is ISS or IDS 5. If I decide that that is CC dV0 by dt, because this is V0, so if I have to charge this capacitor by this current, the maximum current available to me is IDS 5, okay. That value I use and I say I was given the slew rate of dV0 by dt is 10 volt per microsecond, CC dV0 by dt is IDS 5, IDS 5 is therefore equal to, C is 3 into 10 to the power minus 12, 3 puff into 10 into 10 to the power 6, which is given dV0 by dt, which is 30 microamps, or if I use 2.5 it is 25 microamps. So the first parameter I need to know about GM 1 and 2 is I must get the current in M1 and M2, is that clear? So once I know IDS 5, what is the GM value will carry, what current I will require? Half of this ISS by 2. So 25 by 2 or 30 by 2 I can use to evaluate GMs, which I will evaluate next time, and then we will start getting W by Ls. Once I get GM, then I proportionally start getting widths and length ratios. Is that correct? So the first parameter which got me closer to W by L came from where? CC I chose from the phase margin. Slew rate gave me one value of current. From where the other current value I can get? Power dissipation. Is that correct? The temperature is not given, even that can give me another limit. Once I get my limits, I may now say this says 12.5, the other says 15 or 20. I said fine, 20 a higher current I will not choose because low power will be lower than that, so I may choose this current. But let us say that becomes lower than this, then I will choose that value and adjust this value what maximum CC I choose. So I will have to go back and change my CC value to come back here. Is that, let us say that current is smaller than this value, power is first, so now change CC to get to that. Is that clear? So that is the design issue it will start.
Sir,
so it means yes.
Sir, this slew rate is of OPAMP or game stage
because it is not OPAMP, it is essentially V0 is going at the CC output. So the output rises as the capacitor CC charges.
Sir, there is a capacitance C2 also.
But that is not actually charged by this current, it is charged by M6 or M5. Okay, that is the limiting this. Okay, that is the slew rate for the external, where actually we will not use this, we will actually put another buffer stage to drive that. This essentially slew rate is specified for the two stage op-amp, in which output node, which is my M6, M7 base, how fast the CC allows current to come there. Okay, that is essentially called slew rate for the two stage system. What you are saying, op-amp finally slew rate, there will be third stage available, which anyway is a bigger one and which is a push-pull kind. So it will dump huge currents or it will remove the huge currents or huge charge. So then that slew rate is not very important because I am actually dumping the currents heavily from the buffers. Okay, this is very important because this is going to create my next output for the push-pull stage, and that I wish to know how much. Is that okay? So these are the issues which we will discuss further. As of now, I only look for CC charging because that is going to the output node, and that only can provide through the M2 M4 arm, okay, which is the maximum current is IDS 5. So that I charged. See you then.